Welcome, everybody. Good morning. It's my great pleasure to open today's session on trends in analytical chemistry, nanoplastic. And today I would like to discuss with you chemical analysis of nanoplastic, to speak about challenges, advanced method, and perspectives. So let's start. What is plastic, microplastic, and nanoplastic is? So we know that on the one hand side, plastic is lightweight, durable, formable, and help to improve our life enormously. But on the other hand side, we are facing now a problem if plastic, microplastic, and also nanoplastic end up in the environment and food. And if we speak about microplastic, nanoplastic, what size dimension we mean? So under microplastic, we understand particles from 1 micrometer to 1 millimeter. As nanoplastic, particles smaller than 1 micrometer are understood. And for further discussion, it's important to differentiate between primary, micro and nanoplastic, and secondary particles. Primary particles are intentionally produced with desired size and shape. They can be mono or polydisperse. Secondary, micro and nanoplastics are formed in the environment by fragmentation and degradation or through wear or tear of plastic-containing items. So the question whether microplastic and nanoplastic are dangerous is still under consideration, but we have to consider that monomers and additives can leach from plastic particles, and some of them are already proven to be toxic, cancerogenic, or endocrine disrupting. Also, volatile organic compounds can be formed and released due to oxidative photodegradation. Also, micro and nanoplastic can sorb persistent organic pollutants and toxic metals. And generally, more hazard effects are expected from smaller particles compared to bigger particles. And especially for nanoplastic, a lot of concern is about that nanoplastic can penetrate through cell membranes. For example, it was already shown that they can go through gut barrier. Also, due to really large surface to volume ratio, nanoplastic can sorb larger amount of external chemicals compared to microplastic. And therefore, real Trojan cause effect in the transport of contaminants is under consideration. So nanoplastic can be problematic, but do we have it in the environment? Actually, yes. For 5 years already, Alexander Terhalle et al. Show that in fractions smaller than 1 micrometer, nanoplastic in form from polyethylene and also polyethylene terephthalate can be found by using of pyrolysis, gas chromatography, mass spectrometry. Also in personal care product, nanoplastic can be found, for example, in form of polyethylene. And Hernandez et al. Discovered in the fraction even smaller than 100 nanometer. They use Fourier transform infrared spectrometry and X-ray photoelectric spectrometry to confirm that they have plastic. So we have already this problem. Therefore, we really need to discuss it from analytical point of view. And if you have a look at microplastic and especially nanoplastic, we have to say that it's real complex analyte. So we have really broad size range for nanoplastic. It's from 1 nanometer to 100 nanometer. We have different polymer types. It can be polyethylene, polypropylene, polystyrene, polyvinyl chloride, and so on. We have also different shape of these fragments that makes automated procedure really challenging. We have also various additives and sorb contaminants and particles with different agent state. It can be primary and secondary particles or biofuel particles. Therefore, it's real need to develop reliable methods for the analysis of plastic particles in micrometer and especially in nanometer range. And these methods have to include representative sampling, efficient sample preparation, and sensitive and selective identification and quantification. And only then we will be able to find a needle in the haystack. So, do we have the methods which allowed us reliable analysis of nanoplastic? So, till now, not really, because the methods which were developed for the analysis of microplastic cannot be directly transferred to the nanoplastic research, because nanoplastics have really small masses and sizes. Also, methods which were established for analysis of engineered nanoparticles not really fit for purpose, because they are especially focused on inorganic particles. Therefore, existing methods have to be optimized and new methods have to be developed in order to tackle with the problem of nanoplastic. And here, it's really important to consider several points. First of all, nanoplastic in real samples can be at relatively low concentration as mass fraction, and also number of particles can be comparable to the number of natural particles. Therefore, preconcentration and enrichment is really important for proper analysis. Next step, that sensitivity of existing mass-based method can be insufficient, therefore optimization is needed, development of new method, and also combination with efficient preconcentration and enrichment. Also, if we have a look at particle-based methods, most of them are diffraction limited. So it means we can analyze particles only down to approximately 300 nanometers. Therefore, here, application of scanning probe techniques can help, and also approaches which combine information about particle number, size distribution with chemical identification can be useful. We have also to consider that in order to develop some methods to validate it, reference materials which mimic natural or real nanoplastic particles are needed, but they are really rare and no certified reference material exists at the moment. And also level of contamination in nanometer range is significantly higher compared to micrometer range. So it means we have to work in clean room, in laminar flow benches, and blanks are really inevitable. So let us discuss what method can be applied for identification and quantification. Generally, they can be divided on mass-based and particle-based method. Mass-based method provides us information about mass of different synthetic polymers. This information is really important for modeling, for some regulatory procedure. And here in microplastic field, pyrolysis, gas chromatography, mass spectrometry, and thermo-instruction desorption gas chromatography, mass spectrometry are really well established. This method differentiates by maximal analyzed mass. So it is higher for dead GCMS, but with pyrolysis GCMS, lower detection limit can be reached, but it can be pointed out that this detection limit strongly depends on the type of polymer and inorganic fraction. Also, different additional methods were already tested for microplastics, multi-AFM-IR, thermal desorption, proton transfer reaction mass spectrometry. It is also possible to extract nanoplastic with some solvent, and in this case, high-performance liquid chromatography and nuclear magnetic resonance methods can be applied. So with these methods, we can get perfect information about mass of our polymers, but we have particles, and from toxicological point of view, information on particle number, particle size distribution is also important. This information can be obtained with particle-based methods. Here, for microplastic analysis, attenuated total reflection, Fourier transform, infrared spectroscopy was established to analyze particles down to 500 nanometers with near-infrared spectroscopy. Recently, particles down to 50 micrometers were analyzed. A really good established method in this field is micro-infrared spectroscopy. It can be Fourier transform based with focal plane array detector, for example, or quantum cascade laser based infrared spectroscopy. And in both cases, spatial resolution down to 10 micrometers can be reached. So for nanoplastic analysis, they are not really suitable. Analysis of particles down to 300 nanometers can be achieved with Raman microspectroscopy. If we want to perform infrared analysis, we can use optical photothermal infrared spectroscopy, where lowest particle size which can be detected is 500 nanometers. I will present you this technique later. From Raman-based methods, coherent antistocks and stimulated Raman scattering method can be applied. And also for analysis of nanoplastic, secondary ion mass spectrometry can be suitable. So we have a lot of methods for mass-based and particle-based analysis. Sometimes we just need only one of type of information, but really often this information can be combined to get complementary data. So from the field of nanoparticle analysis, we can take the methods for fractionation and characterization. For fractionation, hydrodynamic chromatography, size exclusion chromatography, and field flow fractionation would be really important. For the characterization of particles, to get information about morphological characteristics or aging of particles, scanning electron microscopy combined with energy dispersive X-ray spectroscopy can be applied. It can help to differentiate plastic from inorganic particles and to detect some polymers, for example, polyvinyl chloride. Combination of scanning electron microscopy with Raman microscopy can help us to get chemical and morphological information. Also, one method from nanoparticle analysis, which also Dr. Florian Meyer will present, it's single particle induced coupled plasma mass spectrometry, which allow to analyze nanoparticles. And atomic force spectroscopy coupled with infrared spectroscopy and nano-FTIR can be also useful. So I already listed a lot of methods, but first of all, we need preconcentration of our samples. And therefore, here, different methods have to be considered. I have to mention that, for example, density separation is not suitable for the analysis of or for preconcentration of nanoplastic particles due to colloidal nature of these particles. But here, continuous flow centrifugation can be applied, and by operating of two continuous flow centrifugation, it is possible to separate microparticles and nanoplastic particles, which was shown for palladium-doped nanoplastic particles in the size of 160 nanometers. Another strategy which can be followed for the preconcentration is cloud point extraction. For example, so it all shows that using of Triton X45, it is possible to achieve enrichment factor of 500. And it was used for preconcentration of polystyrene and PMMA particles smaller than 100 nanometers. It is also possible to combine micro and nanoplastic preconcentration. For example, if a glass membrane with 1 micrometer pore size is used, so in this case, microplastic can be separated and nanoplastic later preconcentrating using cloud point extraction. So if we already made preconcentration, what methods can be applied to get information about chemical composition and concentration of plastic. One of advanced methods which I would like to present you, it's thermal desorption-proton transfer reaction mass spectrometry, where hydronium ions used for ionization. And using this method, it was possible to find nanoplastic in Alpine snow. And recent publication from this year report on nanoplastic in North and South poles. So Materik et al. Found different polymers in Greenland from core and sea ice from Antarctica. And the concentration of plastic in Antarctica was even higher. And in all cases, polyethylene, polypropylene, and polyethylene terephthalate was found. But in Greenland, also polystyrene, PVC, and tire were detected. So it's already possible not only work with reference materials, but also find nanoplastic particles in environment. Regarding advanced particle-based methods, I really like to discuss with you atomic force microscopy, infrared spectroscopy. This method, in this method, tunable infrared laser is used, which is focused close to the cantilever, and then if wave number of laser is adjusted to the adsorption band, so photothermal expansion take place, and this expansion is registered by cantilever. And by measuring of this oscillation of cantilever as function of wave number, adsorption spectrum can be reconstructed. Using this method, Pancani et al. Already localize and characterize the nanoplastic particles made of polylactide in macrophages without any labeling. For infrared spectroscopy, of course, we have to dry the samples, but no further labeling is needed for detection of nanoplastic particles. In this case, 200 nanometer polylactide particles were used. Another advanced particle-based method, which I want to present you, is optical photothermal infrared spectroscopy. I'm not sure whether you already heard about it. Okay, somebody already knows this technique. It's similar to AFM infrared spectroscopy, but in this case not cantilever, but visible light. So green laser is used to probe this expansion due to illumination of sample with quantum cascade laser. It means that also chemical information can be achieved with spatial resolution of visible light, and so gap between spatial resolution of usual infrared spectrometry, where it's go down to 10 micrometers, and between nanoscale can be made, and in this case, particle shape and size independent sub-micrometer analysis for infrared can be done. But if we already have green laser, we can also get information about inelastic light scattering, about Raman scattering with second detector, so we can analyze, for example, paint particles. It is particles of coatings which contain pigments, but also polymer parts. And using Raman microspectroscopy, we only can detect pigments because they have pre-resonance signal, but we have really strong fluorescence. But using infrared, we can detect polymer fraction here, so we can really identify these particles as paint particles, so complementary chemical information can be achieved in this case. So I already mentioned that for the analysis of particles, it's really important to have suitable reference materials, but it's not so easy to produce them. So by milling, it's not really suggestible because in nanometer size, these particles are already airborne and it's not healthy to use it. Therefore, different methods for preparation of particles in suspensions were developed, for example, using laser ablation. Polyethylene terephthalate particles in nano size range can be produced. but there are also some more suitable methods which can be applied in each lab. For example, preparation of particles using ultrasonic treatment in alkaline condition. With this method, microplastic and also nanoplastic particles can be produced from polystyrene, polyethylene terephthalate, polyvinyl chloride, and polylactide. Particles and fibers can be produced, and really important, these particles are suspendable because the surface of these particles is aged due to ultrasonic treatment, so they are really similar to secondary micro and nanoplastic particles. So at the end, we can go through the entire roadmap, what we need to perform nanoplastic analysis. So we have to start with analytical question, what information we need about mass of particles, about particle number, size distribution, or we need both information. Then we have to combine different methods. So we have to perform representative sampling and optimize sample preparation with concentration and size separation. And then, depending on question, we can get morphological information, information of size of our particles, and perform identification either with mass-based or with particle-based method, and finalize it with quantification and information. So, to conclude, we have to say that in order to perform reliable nanoplastic analysis, preconcentration and enrichment are really essential. And as example here, I show you continuous flow centrifugation and cloud point extraction. For mass-based methods, development of new method and optimization of existing method is needed. And as new method, I presented you TD-Proton transfer reaction mass spectrometry. For particle-based methods, if we really want to go down to a range below diffraction limit, scanning probe technique can be applied, or we can combine methods which provide us information about particle number and size, and combined with identification methods. So reference materials are inevitable. Here it can be, they can be produced by laser ablation, ultrasonic treatment, but some special particles, for example, palladium labeled particles for ICP-MS or 13C or 14C labeled particles can be used for special application. So what we will have if we will develop this method, first of all, we will provide solid data on nanoplastic occurrence, and these data are required for reliable risk assessment. But it's not everything about nanoplastic. So if we develop method which can be used for the analysis of particles in nanometer range, that can be applicable for another field where chemical information for inorganic and organic particles is needed with information of particle number, size, and shape. So at the end, I would like shortly announce topical paper collection at Analytical Bioanalytical Chemistry, which will come soon. It's advanced in chemical analysis and of micro and nanoplastics, where Dr. Sebastian Primke, Dr. Jennifer Lange, and me acting as guest editor. So submission deadline is end of August, so you still have time to prepare your particles, your manuscript, if you have really good data suitable for analytical bioanalytical chemistry. So if you are interested, please contact one of the guest editor. So, and in the end, I would like to thank colleagues from my institute, from the companies with which we work, and funding, and I thank you very much for your attention. Thank you.
Thank you, Natalia, for this very interesting introduction to the field of nanoplastics, and especially to give us some information on new detection methods.